everyone to the August MicroPython meetup. Tonight we're going to hear Damien talk about MicroPython 1.26, which was released 3 weeks ago, I guess. Something in that order. And then I'll give a bit of a quick news roundup as well. So, Damien, take it away.
Thanks. Welcome, everyone. Thanks for joining. So, there was release of MicroPython 1.26.0 done about 3 weeks ago. So the aim, it was August 10, yeah, so 17 days ago, a bit less than 3 weeks ago. And the aim was to get this out on this. It was a set date, the first week of August, and it was about a week late, which I think is not too bad, because there was a few last minute bugs that needed to be ironed out and fixed up. But the target date was set like well in advance, 3 months in advance, so it was good to be able to hit the deadline pretty well. And the idea moving forward is to keep to a 3-month schedule, and not let any features block that. So it will just be release on this date regardless of what's in, and whatever gets in. So that helps everyone to know when the release is coming out, and that there are going to be irregular releases, so that if something misses a release, a good feature, then it's going to probably be in the next one anyway, which will be close. So in this release, 1.26, there were quite a few things that got in the end. The first one listed here, I2C target mode, which originally would have been called I2C slave mode, where you can create an I2C target device, something that is talked to by the controller, the other side. So MicroPython has supported I2C controller for a long, long time. And that I2C target has been a much requested feature and is now available to use on most of the ports. On the RP2, RP2040, RP2350 at least, they have good support there. ESP32 works a bit, although not on ESP32 original. I'll give a bit of a demo of that to show how it works. There were some other interesting things in this release. Improved floating point support. Probably most people won't notice it, but printing of floats should now be better. So there are many floats, and not all of them print correctly in MicroPython because it's hard to make floats print out correctly. But we've improved that. And the idea is to make it so that when you print a float, if you reparse that float, then you get back the same value. And that has been improved to a very high percentage of floats will do that now, around 98 or 99%. So float printing is better. There are also new ESP32C2 support, which is kind of like the successor to the ESP8266, in that it's small and cheap and doesn't have too many features, but it has more than the 8266. And also the STM32N6, which is like a machine learning AI part from ST. So yeah, that's good to see some new parts. So let me jump to a demo of I2C target mode. So I have 2 Pi boards connected up. I don't know if you can see my video as well, but they're connected with 2 wires, clock and data. Can you see a video, or do you want me to stop? Yep. So 2 boards connected with 2 wires, and on one of them, so I'll use MP remote to connect to one, and on the other one, yep. Okay, so we have 2 boards that I'm connected to their REPL here, and with one I'll make the controller, and one I'll make the target, so master and slave in the old terminology. Actually, it's interesting that NXP, who published the I2C spec, I think it's NXP, they officially changed the name to from I2C slave to I2C target. So if you look at the specs for I2C or I2C, you'll see I2C target actually referenced in the official specs. So that's why we called it I2C target, I2C target. Okay, so on the left, I'll import machine and make a I2C controller, which is the upstream. Okay, so on port X. So if I scan, let me just reset this one because I was preparing this demo and it may still be there. I wanted to show you how I2C. So scan returns nothing at the moment. But if I start to create something, so I2C target on the other side, port X, it's telling me here, actually, I need to provide an address argument. So I can't just simply create an I2C target. I have to say what address it has so that it can be addressed. So address is, say, let's give it address 67. Doesn't matter what you do. Well, there's a range, but 67 is good enough. So now if I scan on the controller side, I can see that address 67 responds, which is great. So the other side, the other board that's connected is responding to that scan. So there's not much I could do at the moment because I haven't really implemented anything here. It's just going to scan. But what I can do to start with is register some interrupts to see what sort of events there are. So I actually target IRQ. Actually, let me define my interrupt handler first. So IRQ handler. So it's going to take some instance, I2C instance, and I'll print out I2C.IRQ.flags. So just print out which flags are set. So that's kind of the trigger or the events that have happened on that IRQ. Okay. So I2C, if I register my IRQ handle like this, okay, so now whenever I do something from the controller side, we should see events appear on the target side. So if I do a scan, I see event number 32. So it's a bit mask, and we can see a list of them. IRQ, so there's about 6 of them. So address match for a write should be, well, there's address match for a read, which is 1, but end write is the one that we received there. Now, I think by default, you only get the ends. So we want more than that. So let's register trigger equals, say, everything. So I'll put in a bit mask trigger is and hard equals true. Okay, so now I'm going to respond to all events. So when I do a scan, I get event 2 and 32. So event 2 was address match write, and event 32 is end write. So it's saying that when I got a scan, the first event was that my address was matched for a write, because we know a scan, well, I'm telling you the way a scan works is that it tries to write to all the devices with a 0 byte length of write. So we'll get an address match write, and then we'll get an end write event because there was no data. If we make it a little bit more sophisticated, so now that we know there's a target device at address 67, let's write something to it. So write to address 67 test. So now we're going to address it, write 4 bytes, and then end. So we should get 6 events. Okay. We have to respond to those events or they won't work. Let me see which one is that. Let's bring it back. Oh, it should be alive again. No device. Come on, device. There we go. He's back again. Okay, so we can, if we make sure we respond to the events, it will act as appropriate as you define it. So the problem there was that when we write to the I2C device, if you don't respond by reading the data, the target will stretch the clock to say, I'm not ready yet to read the data. So the controller wrote the first byte, the T, and the target didn't read it. And so it said, wait, I haven't read it yet. And then that was kept happening. So it just failed. If we want to read the data, we have to write some code to do that. So RQ I2C. So we can print I2C.RQ.flags, and then if the flags and well, we're going to need RQ. Let's do it this way. Read request. Then we need to do I2C.write X, and if it's a write request, we need to do, let's say, print got I2C.read 1 byte. We need to read into a buffer. Okay. It'll have to be global and print got buff. Okay, and buff by array. I'll have to pre-create the buffer. Okay, I see target. And we need RQ handler trigger equals everything and hard equals true. All right, so if we do it.scan and it.write to, let's just try one letter A. Okay, so we can try that again. Okay, so when we write a single character, the first event we got was this address match target.irq address match write was event 2, and then we got an IRQ write request, I think. Yep, because we wanted to write to it. And then our handler here, when we get a write request, we have to read the byte that got written to us, and it printed it out. So it was an A, and then the 32 was the end write. Okay, so now if we try and write AB, we should get both events, hopefully. Yep, so 2, so address match, write byte A, and then write byte B, and then end. So you can see how from here you can basically write any, create any I2C target device that you like. We can also do reads, read from device 67, say 2 bytes. Now, hopefully we're going to get back what we had in our hand. We're going to get 2 X's because we've written some code here that responds with an X. Yes, so we got 2 X's back. And here in the events, we got event 1, which would be an address match read. And event 4 will be a read request because the controller is requesting the read. And then event 16 will be end read. So this back here showed you a very, very simple handler, which will be able to handle any reads and writes. And then we can do reads and writes over here. So we can also do a, it should respond to a read write to mem, which is a more advanced write than a read. So mem will address say 4 and read 2 bytes, address 2 and read 4 bytes. Oh, got it right. Test. Yep. So that wrote to mem test, and you can see test appeared on the other side here with address 2. And if we do I2C.read from mem 67, say address 2 and read 4 bytes. We'll get 4 X's back. But you can see on this side that the first thing we got, I'll try it again. The first thing we got was a write for the address 2, and then we got restart and read 4 bytes. There's actually a fifth because of the way it works. But so this is a very, very general I2C device. Now, if you don't want to implement all those low-level callbacks, you can actually just make I2C target equals machine.I2C target. There's a built-in support for a memory device. So say address 67 and memory equals byte. I'm going to have to create the byte array first. Mem equals byte array, say 8 bytes. And then we can create a, okay, so my I2C target now, I don't have to define an interrupt handler. That's all done for me behind the scenes. I've just passed in this memory buffer, which it's going to use as its buffer to read and write from. So to start with, memory just contains a bunch of zeros. But if I write into that memory at, say, address offset 0, the word test, mem should now be, okay, test. I still have to get rid of that of the IRQ handler. That's still lying around. All right, so now mem should contain test, yes, as the first 4. So if I update that, so say mem equals hello, it's got to be exactly 8, so that's hello ABC. Then if I try and read from the other side, read from mem address 67 is the I2C address, and then offset 0 into the byte array. And if I try and read 8 bytes, I can get back the buffer that I just put here. And the buffer doesn't change on this side. And so I can, if I write test back again and then read it, it's got test in that first 4 bytes because that's what I wrote to. And if I look at it on the other side, you can see it's been updated here. So this gives you a simple way to do the most common I2C target device that you would usually make, which is a memory-based device. So you could put in a huge buffer here or a small one, and you can still respond, as you saw before, you can still respond to events even if you've got this memory buffer. So you can respond to, say, the end write or end read to know when the controller has written or read from the target device. So that's an overview of that feature. The documentation is, if you go to docs, and you look for I2C target, there we go. Yep, it should be here. And there are some examples, what I've just shown you. This is that interrupt handler that I defined, although that doesn't have the read and the write. No, that's just for the end events when you're making a memory device. This one here is the more sophisticated one that I showed at the beginning. So yeah, I think it's quite a cool feature. It's available on all the ports, but as I said, ESP32 not original, but the S2, S3 have it. Okay, so I think for the rest of the things in the release, I'll leave you to read the notes if you'd like to see. There's some more details about things that we have now. Maybe one thing to highlight is that the things have been optimized so that you can create slices without using memory. So MicroPython strives really hard to be able to do things without using heap memory, like adding small integers together, for example, or doing arithmetic with small integers, calling functions, and so on. And one thing that's been annoying for a while that has to use memory is when you index something using slicing. So like this, that normally means to create memory for the slice object A to B, but we've made some optimizations where that object can be placed temporarily on the Python stack or the C stack, and then used and then discarded immediately. So you won't notice any functional change, but hopefully it uses less heap, which means more performant because it's not going to allocate memory and then having to garbage collect it. It also means you can do operations with slicing in cases where the heap is locked, like in a hard interrupt handler, for example. So that was a nice improvement that we had. But yeah, read the documentation or the release notes here. There's quite a lot of cool features like MP remote tree, which is a good way of seeing the files on your board. I can show you a quick demo of that. Maybe MP remote tree, is this the latest version? Yes. So here's all the files on this board, and you can use the -h for human size output, which is, yeah, that's a good feature. I think MP remote DF has been improved. Yes. So it shows you the actual file system type, size, and used, and where it's mounted. So this is getting closer to the Unix output, which I think it gives you quite a lot of good information here. You can tell what's going on. So yeah, lots of good things. And the next release is scheduled for, I think, so August, September, October, November, early November, and there'll be more things there. That is usually listed if you want to track what's going on. You can go to milestones, and then in GitHub there's a milestone for the next release, which has all the things that are scheduled, not necessarily going to make it, but are considered for the next release. Okay, I think I'll stop my sharing there. And thanks, of course, to everyone who helped with the release. Many people, and from all around the world. Very much appreciated everyone's contributions.
Damien, I don't know if you wanted to quickly touch on the Octoprobe stuff and how you use that for this release, because yeah, we've sort of been getting some information about it, but I think people would be interested in just briefly.
This is a stack of Octoprobe boards which are used for sort of hardware in the loop, or at least will be. They are not fully in the loop yet, but so on here you can see it's all labeled. Well, not all of it, but most of them are labeled as to what board is in here. Don't know if that labeling's backwards. ESP32, what is it? S3, Itsy Bitsy, Teensy, yeah, Picos and everything. So each of these boards here is going to test a particular board that MicroPython supports. So each of these Octoprobe boards has a device under test which sits on the actual board. It's very cool hardware, and there's also a lot of software on the other side of it which controls it and makes it so that you can instigate a run. I mean, there's lots to show here. I don't know how much I think Hunt's showed a bit previously.
Yeah, it's just more of like, how many tests are you running on this thing now? Like, because I know that one of the burdens for MicroPython releases was always doing the manual testing, and obviously we're hoping that this alleviates some of that. So
yeah, well, now that testing is easier, there's actually more tests that are being done, which makes it harder because there's a lot of things that go wrong. So it's not like
more stuff.
Yeah, it's like the more you can test, the more you do test, and then it's like, oh, there's so much to test. And then the good thing is you find with so many tests, you're like, well, what's the point of running, like floating point addition on every board, because it's going to work. But you end up finding if you run every combination of every test on every board and all the native versions and so on, you do find the edge cases of like, maybe the floating point operation doesn't fail, but what fails is, the USB on this thing gets overloaded for some reason, or there's something else related to running many tests in a row or something like that, and you're like, okay. So you get these edge cases which just improves overall quality because you're fixing things that you only find from really heavy testing. So the testing has been really great, and it's improving and improving and becoming more and more streamlined. But as I said, then there's more and more stuff being added on top of that. So I think Octoprobe at the moment runs about 40,000 tests across 16 boards, I think, something like that. And that's not even, I mean, MicroPython supports like output of 200 boards. We're not going to test everything. That's impossible. But, well, not impossible, but not really practical at this stage. So we try and test a selection of boards. For the release, I do test more than 16. I've forgotten how many I test, but it's closer to 30, I think. But I'm using Octoprobe to do that now. And yeah, I mean, more of this, we can talk about more of it in a future meetup, because it's still work in progress, but it's going really well, and it's good to have Hans working, pushing this, who is the instigator and creator of Octoprobe. He's really pushing this to make it better, and I'm very happy to help, because yeah, I'm benefiting from it. Are those integration tests? Yes, I can. Well, let me show quickly, Carlos, because that is a good question. We've got to go to reports here. So, so this is the Octoprobe page, and this is a list of runs that have been made. So you can see there's quite a lot so far. And yes, it runs through a self-hosted GitHub action. So if you start a job, you've got to say who you are, and then any arguments you want to pass through, like to select a certain number of tests or a certain number of boards, and then which branch you want to test. So usually you can test a pull request. So say I want to test this pull request here. I can do it, and you just do put my name in there, and then you validate it first, and it checks that pull request is valid, and then it can run with those parameters. Yeah, so it gives you a list of the recent commits, so you know you got the right pull request. And then you press start. I won't press start because there's something else running at the moment. And then it appears on this list here. So this one's in progress, so we can already look at this one. So Hans started this just recently at 9:04. This was started 5 minutes ago by Hans. So here you can see it's a self-hosted runner in GitHub Actions, and you can actually watch the progress of the coming out here. The main thing to look at is here. So there's 15 tests. There's 20 tests total, and it's running test 15. So it counts down. So there's 15 tests left. So I'm not sure how much longer that will take. It can sometimes take many hours. You can see the total runtime, like 5 hours here, 5.5 hours. Yeah, it depends what's going on. Here it's actually running the test 4 times in a row so that it can check which one's for flaky. And if you look at the output of that, okay, so it ran 49,000 tests, even just on a subset of tests. And there's sort of a matrix here of which test passed and failed. Yeah, so each board was actually having 4 tests. Maybe a more indicative one is just like, say, this one here. Didn't take too long. Yeah, so this is the full test suite on 37,000 tests, but 2,500 failed. It's a lot of failures. So there's some things wrong, but it gives you a report of which ones, only of the things that failed. So you can then go and say, well, on this board here, we've got these failures and we have to go and investigate them. And you can click through and see like a test results output and it's full report of what failed and why. Yeah, so this thing doesn't support that test properly. So there's a lot of output here. Okay, so this board here crashed halfway through the test, so it's just got a whole bunch of failures. Whoops. Yeah, which is annoying. So look, there's still a lot of work to make this more robust, but you can see what's going on. So the idea, yes, is that anyone can trigger ultimately it would be triggered automatically on any pull request, but I think that might be a bit ambitious. So at the moment, you just have to manually, as you saw that start page, manually trigger it. When it's more stable, maybe we can put a button somewhere prominent and people can press in a pull request that will just start it for that pull request. I still don't think it should be automated, like go automatically, because there's too many pull requests and it will just overload the system.
Yeah. Not on every push, definitely.
Yeah, yeah, exactly. Not every push. It's like, well, I've got to a stage where, yeah, I've got this thing going and I want to test it because, yeah, not everyone has the hardware. I mean, even I don't have every single board that we support. So,
yeah, I've been thinking, right, it would also be cool is if he could pool the hardware, right? With I've been running self-hosted runners as well for some testing, right? If he could, but the problem, of course, is that requires repo permissions, right? So it would be cool if everyone could supply some hardware and run that in a pool. On the other hand, well, security and repo permissions are interesting in that case because
yeah, true.
a runner has, well, demigod permissions.
Yeah, because you need, I mean, you need permissions here to write back the results to the central
Yeah.
Octopro report server thing. So, yeah.
But perhaps in a Docker repo or something, yeah.
Yeah. Yeah, if we could pull hardware, that would be interesting. I don't think we're at that stage yet. We've got to get everything working. But anyone, I mean, if you're interested in getting hardware, you can Hans Maerke, who's creator of Octoprobe, he's may be able to send you some, or you can even just order them at JLC PCB.
No, he pinged me. I just ran out of time for the last couple of months, right? So I need to get back to him. So yeah, I know him. He knows me.
He's been very good with it.
Ooh. Thanks, Damien. Thanks for that.
No worries.
And thanks for the work on 126. It was I get a glimpse into how much effort you put into this, and it's pretty astonishing.
And I didn't use AI to write the release notes. They're all done by hand. Huh? I used AI only to proofread, and it found like one grammatical error. I mean, there's probably more grammatical errors, but Gemini found only one,
Nice.
which was nice.